Hi, we're going to finish up chapter 17. We're going to talk a little bit more about galvanic cells, and then we'll finish up the very last section, which is on electrolytic cells. So let me share this again. Okay, so we ended up just talking about standard cell potentials. So how do you determine whether or not a reaction wants to take place and whether or not it has a positive cell potential? So those are the same statements. And now we're going to go to thinking about what if our reaction, so when we talk about standard states, that little not sign, that means all solutions are at 1 molar, all gases are at 1 atmosphere pressure, but we often don't do reactions in standard conditions. So now we need to think about how does the cell potential change if our reaction conditions change. So if we have different concentrations and different pressures. So from our last chapter, we saw that delta G for a reaction is related to the standard state delta G by the natural log of Q, which is the reaction quotient. So we learned about the reaction quotient way back in chapter 13. So it's the expression for equilibrium constant, but it's whatever conditions you mix, so whatever concentrations and pressures you have. So if we have that, and we have our new understanding of how a Gibbs free energy change, so using delta G equals negative NFE, and delta G standard state equals negative NFE naught, then we can just plug those in to our delta G. So we take equations on the second line and plug those into the first line and rearrange it. We come up with the Nernst equation, which says the cell potential under any old conditions is equal to the standard state cell potential minus RT over NF. So R is the gas constant, T is the temperature in Kelvin, N is the number of moles of electrons, and F is Faraday's constant. So that set of constants is multiplied by the natural log of Q, the reaction quotient. I prefer that you just use the Nernst equation that's given right there. The next one, if you would want to use this one, converts from log, natural base log, to log base 10, which involves multiplication by 2.303. And then the next equation combines the R, the T, and the F, given that the temperature would only be 25 degrees, and combines all of those with the 2.303, which you have to remember this only can be used at 25 degrees. And I never use this or this. I always just go back and use this. It helps me make sure I don't make a mistake using it at the wrong time. So the Nernst equation, if we have a cell and it's at 25 degrees that has these following concentrations. So it's a copper iron reaction. The reaction's been balanced, which is necessary. Can't get a Q if you don't have the balanced reaction. And we have these conditions that are not standard state. So they're going to take the one with the constant because it's at 25 degrees. So we'll use it here. So first we're going to get the standard cell potential. So it's copper solid being oxidized. So we got the reduction potential out of the table and changed the sign. It's iron 3 plus being reduced to iron 2 plus. And you can look in the table and find that the cell potential for reduction of that is 0.77. So when we add those together, the overall standard state cell potential is 0.43. Now we'll plug this into the Nernst equation. So we have 0.43 minus our constant. In our reaction, it's easy to see there are 2 electrons transferred. So each iron goes from 3 plus to 2 plus, which is 1 electron. But in order to balance that, we had to have 2. So it's a 2 electron transfer. You can also see it from the copper, but if it's a balanced reaction, looking at one, the oxidation or the reduction, should give you the same information. But the copper going from 0 to 2 plus is also showing you it's a 2 electron transfer. So we have our constant divided by 2 log of, make sure you write your Q correctly. So products over reactants. The copper iron 2 plus squared, iron 3 plus squared, and remember the solids left out. So this cell potential, if it was a cell under standard state, would be 0.43, but it's significantly less spontaneous. It's 0.25. Can we make a, we can't. They changed reactants and products, so I can't make a generalization from Le Chatelet's principle, because we always want to remember, we're just looking at reactions that aren't at equilibrium and their movement towards equilibrium. So this particular section, I would just prefer you skip, not because I wouldn't ask you questions from it, but that you don't need a new equation. So the important concept here is that this is how your pH meter works. So if you have a cell that potential depends on H+, it will be able to measure voltage, and if you standardize it, you'll set a voltage to what you know a pH is. So doesn't tell us the chemistry of this cell right here. I'm sure it's in the book. So when we talk more about the pH section, you don't necessarily have to use that section for anything. We'll understand how to do it without deriving new equations. So you can use a measurement of a cell potential to determine an equilibrium constant, which is really, really a much more accurate way to measure an equilibrium constant than what we did in lab. Measuring all the concentrations at equilibrium can give you a lot of error. But if we look at the equation, it's funny they didn't show you exactly where that came from. Let's go back and see where that comes from. So when you look at the Nernst equation, if your reaction's at equilibrium, so look at the Nernst equation right in the middle. If your reaction's at equilibrium, there's no desire for the reaction to go forward or backwards. So there's no potential for electrons to move one way or another. So the potential of the cell should be 0. So if you set this equal to 0, when Q equals K, and rearrange it, you get the equation that they're giving you right here, where delta G is equal to negative RT ln of K. So you can rearrange that equation and show that to yourself. They actually did it another way. They just took what we did last chapter, plugged in your definition of delta G naught to figure out the relationship between E naught and RT. Both ways will give you the exact same thing. You can measure an equilibrium constant if you know the cell potential. And this is just reminding us about what we know. When K is small, the reaction doesn't have much of a desire to go forward. You have fewer products and reactants. If K is large, it's the opposite. So just relating that now to what the E0 would be. So cell potentials and equilibrium constants. So this is what I was just saying. You can measure equilibrium constants like you did in lab with the indicator. You can just truly measure the concentration ratio, which sometimes gives you a lot of error. You can do it from thermodynamic data. So delta G, that D right here in equation 2 should be a delta. We can measure the equilibrium constant if we can measure delta G. And now we see that we can also measure the equilibrium constant if we can measure the standard state cell potential. So 3 different ways to measure equilibrium constants. And so this is helping tie together everything we did in 13 up to 16. So the next thing in this chapter is just a bunch of examples of batteries, all of which you're probably familiar with. The lead storage battery is the battery that's in your car, and it has an interesting chemistry when you look at it. The reduction side and the oxidation side both form lead sulfate. So that's why you can recharge your battery in your car for a long time, because as the reaction takes place, you get solids building up on the electrodes. And then if you just put electricity in, which your alternator does on your car, you can charge it back up because these solids are at the surface and you can force the chemistry backwards. So it's a good battery for being able to recharge it. The problem is if your car, if your battery's old and this lead sulfite chips off as you drive and bumps around, then it will be laying at the bottom of the cell and it won't be on the electrode surface, so you no longer can recharge it. So there comes a point at which a lead storage battery no longer can be recharged. You have to get a new one. So when you look at these chemistries, I don't want you to memorize the chemistry of any of the batteries or electrolysis processes, but just know if I give you a lead storage battery chemistry, be able to use it in answering questions about cell potential, etc. So this is just another example of a battery. And they're not necessarily giving you the sum of those two, but this particular one has an aqueous solution in it. Some of them are completely dry. So this is just another type of battery. By the picture, you know that that's the battery that you use like in a flashlight, a regular old, it's a D, I think, can't remember. So here's another example of another kind of battery. Notice this one, that the hydroxide cancels on both sides. So when you add those two together, it's a different metal. But the important thing with this one is when you add those two together, you get all solids in the overall reaction. And so the voltage is very stable because it's only dependent on those solids, and it doesn't change as like the OH minus concentration would change because the OH minus actually cancels. This is the lithium battery that's in your computer, and lithium batteries are nice because they're light. So some of these other things, especially going back to lead, they're very, very heavy, and they're also very, very toxic. A lot of people die from lead exposure from these batteries being improperly disposed of. So they're heavy, they're toxic. So as you look at these chemistries, you want to think about people are trying to find lightweight. So lithium is a good example of that. Lightweight, cheap, non-toxic things to serve in your oxidation and your reductions. The little section on corrosion is interesting. Read through that to actually know that it's actually a redox. It's a little electrochemical cell. Everything is important. So you have to have the iron, but you also have to have the water and the oxygen in order for this to take place. So I might give you this as an example, but I'd give you the chemistry. You don't have to memorize the chemistry of corrosion. So this talks about how you can compete with something that's easier. So if you go back here, this is oxidizing iron. But if you can find a metal that's more easily oxidized and coat your iron with it, then it will first be oxidized. So if you can put something on the surface that's oxidized easier, then it will be oxidized in the metal in your car. The iron will be fine. So that's the process of galvanization. So if you put zinc on the surface, if zinc is oxidized easier than iron, that will save your iron base there because it has the galvanization or the zinc metal on the surface. And this is just showing you why. So if zinc has a bigger negative potential for reduction, then that means it has a bigger positive. They should have actually done that because it's the process of oxidation that we're talking about. So this would show you that there's a plus 0.76 voltage to oxidize zinc versus only 0.45 to oxidize iron. So oxidation is the negative of these reduction processes. So this just goes through how you can prevent it, looking at that process of coating the metal. And now we're going to talk about the last kind of cell, Take a little break before you do this though, and work problem 713, which allows you to calculate a K, knowing the cell potential, and then come back and we'll talk about this slide and the rest of them on electrolysis. So electrolysis also looks at reactions that aren't at equilibrium, but now you're trying to make a reaction go the opposite way that it wants to. So the process of using electricity, which is the same thing as doing work, to bring about a chemical change. So if we have a positive standard or a cell potential, delta G will be negative, and that's a galvanic cell. Same thing as thinking about it's a battery. It's a system that can give you electricity. If it isn't spontaneous, then the cell potential will be negative, the delta G will be positive, and in order to get that non-spontaneous process to happen, you have to put work in. And in this case, because it's a redox reaction, we put electrical work in. If your cell potential is 0, delta G will be 0. The reaction's at equilibrium. Same thing as saying your battery is dead. You can no longer get any work out of a system that's at equilibrium. So this is showing you some examples of some of the processes that we use in order to get some of the resources that we want. So chlorine gas is used for a lot of things, purifying water, just lots and lots of uses for it. But the common form of chlorine in the environment is chloride. That's the way chlorine likes to exist. And so we need to make chlorine gas from chloride. And sodium also, there are lots of uses for solid sodium metal. So the common form for sodium in the environment is Na+ as the the single charged cation. So we can have a reaction here where we force electricity the opposite way. So we force electricity to make the electrons go from the chlorine to the sodium, making them back into the neutral. The spontaneous reaction for this would be the backwards reaction. So the battery pulls electrons from the anode and pushes them into the cathode. So you're doing electrical work. So we don't have a light bulb being lit up. Instead, we have some source for forcing the electricity. The other thing that's interesting about this is oftentimes you can't carry out a reaction in water because there'll be a competition. Maybe something in water, the hydrogen could be reduced or the oxygen could be oxidized at a lower voltage. And so you wouldn't get your sodium metal and your chlorine gas. So a lot of these have to be melted down ionic compounds, which have to take place at pretty high temperatures. So if we did try to do this process in water instead of melted sodium chloride, what you see is that it's going to be easier for water to be reduced than it was for the sodium. And so you'll get sodium and you'll get hydrogen gas, but you won't get the chlorine or the sodium. Did I say that? You'll get chlorine and hydrogen, but you won't get sodium neutral metal. So this is the reaction that you guys will do when we use fuel cells the final week of the class. You can use electricity to make water into hydrogen and oxygen. And then that hydrogen is a really good source of energy. Essentially, you've stored energy in that hydrogen. This is just another picture. And once again, don't memorize any of these. I'll give you the chemistry and you might have to use it in some discussion or calculation, but you don't have to remember it. So this is another way to make sodium metal. And this is an interesting one because this one shows us that you don't always need a salt bridge. So in this case, you have a cation permeable membrane. So you can just separate the two chambers so that as the charge builds up, negative on the right-hand side, sodium cations are the right size to go through. And if it's charged properly, then the anions won't go through. So you can keep that charge balance often with a membrane that selectively lets some particles through rather than having to have a salt bridge. Here's our production. This is a really big one. Aluminum in the US. I can't remember. I think it used to, I want to say 6% of our electricity goes to making aluminum. So when we think about why, we take aluminum out of the ground as Al2O3. So that's the ore form of it. And each of those aluminums has a +3 charge. So to make a mole of aluminum, you need 3 moles of electrons. So it's very, very electricity intense to make an aluminum can from the rock. It's much, much, much less energy just to melt down the can and make a new can. So recycling aluminum is probably one of the most important resources to recycle, because this process of making it from the raw ore is extremely energy intensive. This one shows you how you can purify copper. So same exact thing. You take pure copper on one side, impure on the other, and you force a redox reaction so that the copper leaves this side and goes to this side. And when that happens, it goes to the pure side and you can purify your copper. So that's electrolysis. So in order to do these calculations, like how much electricity does it take to make an aluminum can, we have to think about the process. So current is the coulombs that move in some unit of time. So if we have the unit of amp, which is right here, A is for amp, AMP. If amp is in coulombs per second, then if you multiply by seconds, you get the total number of coulombs that move in a unit of time or in your amount of time. And so you have to convert that to moles of electrons to compare that to the quantity of any substance you're making. So coulombs divided by Faraday's constant converts from this unit of charge to the number of moles of electrons you would have. Oops. So they are not going to go through an example. Why don't you try 1722, and I will certainly go through an example in my recorded problems on how you might determine what quantity of metal you can make using how much electricity using electrolysis. So that is the end of Chem 108. We're going to do some projects and see how this all applies to things you're interested in. And we're going to do some work with fuel cell cars next week. But other than that, that's all the new material.